Hello everyone. Today we are going to find the Laplace transform of a damped sine wave. Our function is f of t equals e to the minus at times the sine of omega t. So what's our strategy for tackling this? We are going to use a powerful property called frequency shifting. The key here is something called the first shifting theorem. This is a fantastic shortcut for any function that's being multiplied by an exponential term like e to the minus at. Here is what the theorem says. If you know the Laplace transform of some function, let's call it g of t is g of s, then the transform of that same function multiplied by e to the minus ap is just g of s plus a. Essentially, all we have to do is find the transform of our base function and then just shift it by replacing every s with s plus a. It's a really neat trick. Alright, let's start with step 1. We need to identify our base function. We are going to compare our function to the general form from the shifting theorem, which is e to the minus at times g of t. Our specific function is f of t equals e to the minus at times the sine of omega t. Looking at these two, it's pretty clear what our base function g of t has to be. By direct comparison, we can see that g of t is simply the sine of omega t. We can really see this relationship visually in these two diagrams. The top graph shows our original function f of t, which is the damped sine wave. You can see how the blue curve oscillates like a normal sine wave, but its amplitude or height gets smaller and smaller as time goes on. This decay is highlighted by those red dashed lines that form an envelope around the wave. In contrast, the bottom graph shows what we've identified as the base function g of t. This is just a standard sine wave that oscillates with a constant unchanging amplitude. So our original more complex function is really just this simple sine wave being squeezed or dampened over time. Moving on to step 2, we need to find the Laplace transform of our base function g of t, which we now know is the sine of omega t. The good news is that this is a standard result that you can find in any Laplace transform table. The Laplace transform of g of t, which is the Laplace transform of the sine of omega t, gives us a function we'll call g of s. And that known transform is g of s equals omega divided by s squared plus omega squared. If you look at the figure on the slide, you can see a plot of this transform function g of s. The horizontal axis is our variable s, and the vertical axis is the value of g of s. The function itself is that smooth blue bell-shaped curve that's symmetric right around the vertical axis. It has a sharp peak where s equals 0 and then it slopes downward as s moves away from 0. This visual gives us a nice idea of how the sine function's energy looks in the frequency domain. Now for the final step, we just have to apply the shifting theorem. Remember, the theorem states that the Laplace transform of e to the minus at times g of t is equal to g of s plus a. We already have our result for g of s from the last step, which was omega over s squared plus omega squared. To find g of s plus a, all we do is substitute every s in that expression with the quantity s plus a. When we do that, we get g of s plus a equals omega divided by the quantity s plus a squared plus omega squared. And that's it. This is the Laplace transform of our original function e to the minus at times the sine of omega t. So let's put it all together for our final answer. The Laplace transform of the damped sine wave f of t equals e to the minus at times the sine of omega t is omega divided by the quantity s plus a squared plus omega squared. This diagram here does a great job of showing what this frequency shifting looks like. The plot shows two curves on the s-axis. The original transform g of s is that dashed gray curve centered right at the origin. Our new transform g of s plus a is the solid blue curve. As you can see, the blue curve has the exact same shape as the gray one, but it's been shifted to the left. The red arrow labeled minus a points from the peak of the original curve to the peak of the new blue curve, perfectly illustrating that shift along the s-axis.